Yeah, we can start.
So, welcome everyone. This is Aditya from Department of Physics, IIT Kanpur, and I welcome you all to this uh, colloquium by uh, Indian Physics Association. And before we start, let me thank IPA and Professor Nanal for giving us the opportunity to hold this colloquium. And with that, also invite Professor Nanal to say a few words about IPA, introduce it to the audience. Professor Nanal.
Thank you, Prasaditya, and thank you to the Department of Physics, IIT Kanpur. We are grateful to you for hosting this colloquium. I guess many of the people are familiar with IPA, but let me take a moment for the newcomers and introduce IPA to you, Indian Physics Association. I hope you can see my screen. Founded in 1970, the country, for exchange of the physics ideas and acquainting the younger community with the new developments in the physics. The information about IPA and its activities is available on its webpage, and keeping up with times, IPA has a presence in the social media, both Facebook and Twitter, and also on the YouTube channel. Most of the last events from the last 2 years for the IPA are available on the IPA YouTube channel. IPA has about 47 chapters and more than 4,000 members. This picture shows kind of the spread of the IPA across the India. This, as I said, the goal is to liaise with the physics community, and this is done through various special lectures. IPA also liaises with national bodies like academies and the other societies. IPA gives out biennial awards to young and distinguished scientists. It also has international linkages. We have an MOU with APS, Institute of Physics UK, the Italian Physics Society, and we are a member of Association of Asia Pacific Physical Societies. We organize programs together with these societies. So IPA IOP has an exchange program running over more than 2 decades. On alternate years, the speakers from India goes to UK, and from the UK they come to India. In India, these lectures are known as Cockcroft-Walton lectures, and in UK they are known as Homi Bhabha lectures. In the last year, through the initiative of the APS International Division, we organized 2 joint events with the APS, IPA APS. One was for the younger people on publishing with APS, and one was what we call a gender event towards the gender equity, the brainstorming, looking for new ideas. IPA has also endorsed the global effort for the role of physics in green economy. IPA publishes a quarterly news bulletin. This is available on the website under the physics news. And these are some special issues which are brought in from time to time. So this was an issue which was on SN Bose. Last year, we brought out an issue on Dr. Bibha Chowdhury, one of the first woman experimental particle physicists of the country. In the physics news, we have started new column. One is Meet the Physicists, so where we feature both young and senior physicists, and they tell you what they are doing in physics and why they do the physics. So if you would like to be featured in this, please let us know. We also feature a department, and since IIT Kanpur is one of the oldest departments and has produced many noteworthy alumni, I hope they will soon will soon be able to feature them. The recent issue, which is published just yesterday, is on the climate science, and I urge all of you to visit the web page and look at this. This brings out many different dimensions of the climate science. The current office bearers of the IPA are Professor Ramakrishnan, Director TIFR, who is the President of IPA, Professor Tanushree Dasgupta, Director SN Bose Center, Kolkata, who is Vice President of IPA, myself, General Secretary, Professor Samit Mandal from Delhi University, Joint Secretary, and Dr. Aradhana Srivastava, Treasurer. A few years back, IPA has set up Gender in Physics Working Group, a very important step to achieve the gender equity in physics. And these are currently the members of the group. The current chair is Shurabati Goswami from PRL. The past chair was Prajwal Shastri. Again, I would urge you to visit our webpage to look for more activities. Gender group organized a first ever conference in Hyderabad in 2019, where the gender-related issues were discussed. So the physicists and the social scientists came together to do that. So that was a unique feature. And next year in 2023, we will co-organize the IUPAP-sponsored International Conference on Women in Physics in India. This will be held online and will be organized by Gender Group and TAFA. So if you like to join IPA, please visit the registration portal and you can just make an online request for it, and IPA member needs to forward you. So please, if you have any issues, send a mail to any of these addresses. I will put in the web page and the email addresses in the chat box. So this colloquium series was started in April 21 with the idea of also focusing on innovative technology and applications. And we have had many interesting talks in the series. And today's colloquium also will be one more in this series by Dr. Surajit Dhara, and we look forward to an exciting talk. So thank you all for attention. I look forward your participation in all IPA activities. And over to you, Prasadit.
So, thanks, Professor Manan. With that, let me very briefly sort of introduce the Department of Physics, IIT Kanpur. Although, as mentioned earlier, it is one of the well-known and oldest departments within IITs. At present, we have more than 50 faculty members working in different areas. We have about 150 PhD students. Right? The area of research varies from experimental condensed matter, soft matter, complex systems to plasma accelerator, and then on the theoretical side, about optics, photonics, and then on the theoretical side, high energy physics, biophysics, cosmology, and theoretical condensed matter physics. Teaching is an important part of our department. We run 4 courses at UG and PG level. Bachelor of Science, that's a 4-year degree. Bachelor of Science plus Master's, an integrated 5-year program. A 2-year Master's program, 2-year MSc Physics, and a dual degree program, which is MSc plus PhD. Our usual intake is, at present, it's about 100 students per year across these different programs. Anyway, more details are there available on the IIT Kanpur website. And if you are interested, you can always send a mail to the head of department or any of the faculty members and get in touch. Okay, so with that, let me take the opportunity to introduce today's speaker, Professor Surajit Dhara. He is from School of Physics, University of Hyderabad. So Professor Dhara did his PhD from Raman Research Institute, Bangalore in 2003-2004, and subsequently he was a postdoctoral fellow at Department of Organic and Polymeric Materials, Tokyo Institute of Technology, Japan. After which he joined University of Hyderabad. He is recipient of several accolades. Just to mention a few, he received the Michi Nakarize by the International Liquid Crystal Society in year 2010. NS Satyamurthy Memorial Award, which is given by the IPA to young scientists in year 2012. After that, he has received the DST Stone Jayanthy Fellowship in 2016, and very recently in year 2020, he was awarded the coveted Shanti Swarup Bhatnagar Prize in Physical Sciences. His area of research or research interests are in topological defects in liquid crystals, photonics of liquid crystals, colloids and droplets, and rheology of complex fluids. So with this, I would like to invite Professor Dhara to introduce the audience to the fascinating world of soft condensed matter physics. Professor Dhara.
Surajit, you are muted.
Okay.
Dr. Surajit, we can't hear you.
Can you hear me now?
Yes.
Okay. Okay, just a minute. Sorry. Just a minute. Sorry, this does not say it. Okay, is that now seen? Screen? Yeah. Right? Can you hear me also?
Yes.
Okay.
Yes.
So at the outset, I would like to thank Professor Nanal for the invitation and also IPA. And I thank Professor Aditya for kind introduction. I'm going to talk today. Sorry, there is some problem. Wait a minute. Sorry, I think there are some other slides. Yeah, it's okay. So today I'm going to talk on the exploitation of topological defects in liquid crystals. This presentation has two parts. In the first part, I will be talking something which was done by my student Zuhail, who is presently an assistant professor in Calicut University. And the second part of the work was done by these two bright students, Dinesh and Devika. And the theoretical support for this work was provided by Sriram Rameswamy and his student Swapnil. And of course, funding was from Department of Science and Technology. So these topological defects are actually their singularities, and which cannot be removed by continuous deformation of the order parameter. So the singularities are basically a code for physical system where the order parameter goes to 0. And generally, these topological defects are characterized by a integer valued winding number, which are also called as defects. And these topological defects have been studied in various branches in physics, starting from cosmology to condensed matter, optics, and active matter, and even in liquid crystals. They have different names in different fields. For example, in cosmology, these topological defects are actually called cosmic strings. And these cosmic strings, it is believed that these strings actually are produced in the early universe, when the universe, after the Big Bang, when the universe was going through several symmetry between phase transitions, these cosmic strings were created. And it is also believed that, in fact, it was introduced by Hubble, and it is believed that today's large-scale structure of the universe is partly due to these cosmic strings, although these strings are not experimentally detected so far. And in optical field, they are called optical vortices or phase singularities. For example, this is a polarization distribution in 2D of a random 2D polarization field. And we can see here that these are the points where these polarizations cannot be defined, these white dots, okay? And so if we go around this point, the phase of this light increases, but at this point, the polarization, this phase cannot be defined. And in solid crystals, or in condensed matter rather, they have defined names depending upon the material. In solid crystals, actually, they are called dislocations. In fact, you can see this is a high resolution TEM image of a solid crystals. So we can see that everywhere this periodicity is well defined except this region, which is marked by white boxes. Okay, and if you look at this FFT, it clearly shows that one or additional plane is introduced, and this is the point of dislocations. And dislocations actually characterized by a Burger vector. So when you go around these points. So in active matter or in liquid crystal, they are called disclination. This movie actually shows that this is a basically turbulence of microtubules at the polyethylene water interface. And you can see the plus minus half defects are continuously forming, and they are annihilating, and they are also moving in the space. So these defects are actually in condensed matter. They are very crucial, particularly for solid materials, for determining their mechanical properties, particularly in steels. Okay. Now, however, in the context of liquid crystal, these topological defects, or rather, any kinds of defects are sort of unwanted in liquid crystals. Okay, because displays should be in this liquid crystal displays, the liquid crystal molecules should be uniformly aligned without any defects. Now, let me briefly introduce what is liquid crystals. So, liquid crystals are basically orientationally ordered fluid made of organic molecules. So, these are some example of organic molecules. This is an organic molecule having rod shape. They could be bend shape, or they could be disc-like. And so, what is important from that you can notice is that safe anisotropy of the molecule is essential to get liquid crystalline phase. In fact, these disc-like molecules tend to form this kind of structure, and you may know that this phase was actually discovered in 1970s by Professor Chandrasekhar at Raman Institute. This is a new branch in liquid crystals called discoid liquid crystals, and that find a lot of applications in photovoltaics and other things. Now, coming back to the liquid crystals which are used in liquid crystal displays in daily life, those liquid crystals are called nematic liquid crystals. This is what nematics, metic A, metic C, basically they are Greek name, and they basically indicate defined phases. So nematic is one of the simplest phase in which, for example, the rod shape molecule on an average oriented in one direction, and the direction I call director. The word I will be using again and again. So director means the director means that the orientational ordering of this molecule in a particular direction. And as we can see that since this n and minus n are physically equivalent, therefore this is a polar systems. Now, if the translational symmetry of the nematic is broken, we can actually introduce what is called this metic, the layered system. In this picture, you can see the on an average, the central mass of the molecules are in a layer, and this is called metic. So one can define a density wave in this direction. Okay, and further symmetry can be broken to get a tilted phase of metic. This is called metic C phase. And so there are more than 40 such defined phases in liquid crystals are known, but this liquid crystal which is used in displays are the simplest one called nematic, which has only orientational order. Now, those who have not seen liquid crystals, this is the image of a liquid crystal, liquid room temperature liquid crystal. You can see this is a turbid fluid, and this is turbid because it strongly scattered light. And in fact, it took nearly 20 years for the theoretician to understand why liquid crystal is so turbid. Now, coming back to the experiment, so if you look at the liquid crystal and you need to use optical polarizing microscope, this is a simple microscope with additional polarizer analyzer, which are kept in the cross position. Now, if you look at the microscope image, you see there are some dark lines, okay, or threads moving around in the sample with a lot of beautiful colors. This color between two cross polarizers arises because of the phases, okay, in interference of the and because of the phases, because the material is a birefringent, so any minus n is a birefringent. Now, what is important is that there are some these black threads. There are some points where it seems to be entangled, okay, or twisted. These points here and there, these are actually defects in liquid crystal. So the defects, so it means in liquid crystal like that where the order is, so everywhere we have an order, okay, and we can also define the orientation of the molecule except these points. And these points, the order parameter goes to 0. And this defect has a core, as I said earlier, this typical core size is of the order of 10 nanometer. Okay. And so therefore we cannot see the defect, but we can see the effect of the defect. It is a far field distribution of the director or these molecules around the defect. Now, if you look at, let's say, one defect, and as I said that these defects can be characterized by integer valued number, which are also called winding number or strength of the defects. So the strength of the defect liquid crystal is defined that if we go around this point, let's say this is a defect point, and if we go around this circuit, 2 pi angle, how many times or how much angle the molecules of the director rotates. In this case, you can clearly see that as I go 2 pi, this molecules also rotate by 2 pi. Okay. Therefore, the winding number is 1 plus 1. If it is the sense of rotation is same, then we say plus 1. So this is the example of a defect, and with a plus 1, these plus 1 defects are called radial hedgehog, which means as if these lines represent the molecular orientation, okay, or the director. So the next slide onward, I will be using lines instead of molecules. So these lines represent that this is a radial hedgehog, and this is a defect where the director orientation cannot be defined. Similarly, we can also have a -1 defect, okay? And you can see as you go in one direction, the director rotates by 2 pi, but sense of rotation is opposite. So these are actually point defects, +1 and -1. Similarly, we can have line defects where the strength of the defects could be +half or -half. For example, if I start from here and go 2 pi around this, you can see the liquid crystal's orientation has rotated by pi, okay? And therefore, it is a half defect. So the half defects are generally lines. So it is also possible to stabilize defects of much higher strength, like 2 + 2 - 2 or so. But since this elastic energy density increases square of the defect strength, such defects with higher strength are not generally observed in liquid crystals. Okay. Now, the liquid, as I said, the liquid crystals. So it suggests that they have some properties like liquid, and they also have some properties like solid crystals. In general, the liquid crystal, the order parameter is a second-rank tensor, and which is written in as the Q alpha beta. So where S is a scalar order parameter, and this part in the bracket takes care of the spatial variation of this the director. Now, since the order parameter is second-rank tensor, the consequence is that most of the physical properties are also second-rank tensor. For example, dielectric constant is a second-rank tensor. Conductivity, stress, and elasticity are tensorial in nature. So if you take a simple liquid crystal which has a uniaxial order, that means having a rotational symmetry along this axis, and this is called uniaxial nematic, we can have optical anisotropy, or they call birefringence, depending upon the polarization parallel or perpendicular to this director or this orientation. And similarly, if we measure the dielectric constant parallel and perpendicular to this the symmetry axis, we can get dielectric anisotropy. Similarly, we have conductivity anisotropy. This conductivity in liquid crystal is due to the impurity ions, which are free to move under electric field, and mostly they respond to the low frequencies. Okay, so we can see that most of these physical properties are anisotropic as expected because of tensorial nature. Another very important property of liquid crystal is that elasticity. Okay, since they are fluid, small external force actually can create elastic deformation. That is the deformation of this molecular field or the directed field. So any deformation sort of can be thought of composed of 3 basic deformations which can be observed in liquid crystal. Is this called splay, twist, and bend. Such deformation costs energy, and this corresponding elastic free energy density can be expressed by this equation. So you can see this is that the K11, K22, K33 correspond to the elastic constant for these deformation to create in the liquid crystal. Now, if you look at this typical magnitude, since this is a curvature elasticity, this elastic constant dimension is force 10 to the minus 12 Newton. It's very, very small. Therefore, small amount of electric field is good enough to create a large distortion. That is why today's liquid crystal displays are there. Okay. Now, the question is, okay, so what happens if I sort of disperse foreign particle in uniform liquid crystal? So this is a liquid crystals, and this is a director, the average orientation direction. Now, if I drop or disperse foreign particles, okay, what happens? So what we expect is that foreign particle will create some elastic distortion in the uniform medium, and that energy should be proportional to K into R. So K is the average elastic constant. Assume that all elastic constants are equal, and R is the size of the particle. So with this elastic energy increases with the size of the particle, but subsequently, since the liquid crystal molecules, liquid crystal is surrounded by the particle is surrounded by the liquid crystal, the surface energy also will grow up. And assume the W is the surface energy per unit area, so it will increase with quadratically with size of the particle. Now, if you compare these two energies, we can define a length called Digens-Clement length, which is called lambda W by K, and it depending if you put the extreme values of these energies anchoring the W and also K, we can find that lambda could be of the order of 0.1 or 10 micrometer. What is the physical meaning of that? If you have particles which are much smaller than this 0.1, that means of the order of, let's say, nanoparticle, it will not create any elastic deformation. So this is the case. So if R is very, very small, then this lambda, the nanoparticles will not create any elastic deformation of the uniform field. Please, again, I remind you that these lines represent this director field or the molecular orientation. Okay. But another important consequence is that these liquid crystals can be used to self-assemble this nanoparticle in like a chain or so. And these physical properties of the liquid crystal will not only be due to the liquid crystal itself, but also due to the properties of the nanoparticle. For example, by dispersing magnetic or ferroelectric nanoparticle, we can manipulate this physical property of the liquid crystal quite a large range. So this kind of liquid crystal, this nanocomposite, is useful for many applications. Now, my concern in this talk is that what happens when you disperse a particle of the order of few micron. That is, the particle size is bigger than this lambda, which is basically a microparticle. Now, as we expect that particles are bigger, the liquid crystal molecule has to be anchored. Either it is perpendicular anchor or it should be planar anchor. This kind of perpendicular anchor will give you elastic distortions called splay, and this kind of planar element will give you distortion called bend. And this distortion costs energy, and that energy you can write in this way, assuming the delta n is a deformation from the uniform orientation, which is small. Okay, and let's say elastic constants are also equal, so you can get the elastic energy due to the deformation created by the particle. Now, assume that initially the liquid crystal molecules are oriented uniformly in the x direction, so n is basically 1 in ny and nz. Now, if we minimize this equation, we get this Laplace equation, and solution of this Laplace equation is given by this. So this is something very interesting, because what you see, this equation looks like this equations, the multiple expansion in electrostatics. Okay, it has a monopole, dipole, and quadrupole terms. What does it mean? That if you disperse a foreign particle in liquid crystal, it will create elastic deformation, and the transverse component of the deformation will look like, transverse means x and y and z component, will look like similar to the electric field lines as you see in electrostatics. That is, when you put a charged particle in a uniform electric field. Now, what is the consequence? In the experiment, you see, so if I have a spherical particle, let's say silica particle, and to begin with, I had uniform lines, means the molecules was oriented uniformly along this direction. But since these molecules are perpendicularly anchored, these particles act as a radial hedgehog. Okay, as if the lines are coming out from the center. Therefore, each particle acts as a virtual defects of topological charge +1. Since the boundaries are at infinity, this demands to have a topological charge conservation, it will demand another negative defect or -1 defect, and this is what exactly you see that this is possible. That means when you put a spherical particle in uniform liquid crystal, it will induce a defect of -1 in the vicinity. So this is a -1, and particle acts as a +1 defect. Therefore, this is like an elastic dipoles. And this, since it's a microscopic particle, you can easily see under microscope. This is an image taken in cross polarizer, optical polarizer microscope. And in fact, even in CCD image, you can see there is a dark point. This dark point is basically defects. Okay, these defects is having strength of -1. So the particle is acting as a +1 defect virtually. This is actual -1 defect induced by the particle. Therefore, this is elastic dipole. Now, this point defects actually can be you can play with this point defect and force it to move towards the particle, and this point defect of -1 can be opened as a loop, and that is called a loop defect, or which is called as a Saturn ring defects. The Saturn ring is at the equator, and this defect has a -1/2 strength. As you know, the topologically -1/2 ring defect is equivalent to a -1 defect. Okay, and this kind of ring defects can also be seen under microscope. So you can see these rings. The ring is clearly seen, which is on the equator of the particle. Okay. Now another possibility is that instead of perpendicular, these two defects, that's elastic, these ring and point defects occurs when you force the liquids and molecules to orient perpendicular to the surface of the particles. But suppose I do some chemistry and make the particles, the molecules parallel to the surface of the particles, then what happens? This induces what is called boson defects. These are basically -1/2 defects to antipodal surface defect. This is -1/2, this is also -1. Okay, and these defects can be clearly seen under optical microscope. So this particle, the spherical particle test with a ring defect and or with a antipodal surface defects, these are called elastic quadrupoles. Okay. Now, these particles in the liquid crystals experience long-range interaction. So, in this movie, I show you that these two particles, and then as you just kept at some distance, with progressing time, they approach each other. So these are basically two elastic dipoles, collinear. They have an attractive interaction, and this interaction potential is quite large, few thousand kVt. Of course, they can be attractive or repulsive depending on how they approach. These are different configurations possible. The point is that the interaction potential is few thousand kVt. Therefore, this boundary motion or thermal fluctuations cannot separate two particles when they are formed. Okay, so that means their binding energy is quite strong. Similarly, we can have a pair interaction of two quadrupolar particles having ring defect, and again we can see they have strong binding energy. And if you look at this interaction potential that involves theta, that theta is angle between this center to center with respect to the liquid crystal director. So therefore, how the two particles approach each other, that will dictate they're attractive or repulsive. Now, if you recall our experience in the particles dispersed in isotropic solvent like water, then we know that they have mostly short range forces, either the van der Waals forces or steric or maybe Coulomb forces. Okay, and so what is the important point is that this colloidal particle in the liquid crystal, they induce topological defects and they have long range elastic interaction, and which is much larger and stronger than the conventional colloidal interaction known in isotropic solvent like water. So now I'll show you that this the beauty of this defects in liquid crystal is that you can actually manipulate with the focus laser beam or laser tweezers. So let's say this is elastic dipole, and I will show you that this elastic dipole can be converted into elastic quadrupole, okay, and vice versa. This in this movie, this is the elastic dipole. There is a point defect, and we use a laser tweezer, and so the liquid crystal director is in this direction. And you can see as time is progressing with the laser field, this point defect is melted, and then we suddenly quench the field in a particular manner, and that gives rise to a ring defect. You can see the two black dots. This is basically the ring defect. Okay, and so that means elastic dipole to quadrupole transformation is possible. This is also topologically allowed because, as I said, -1 point defect is equivalent to a -1/2 ring defect. Okay, such conversion therefore is allowed. Another interesting feature we can show is that we can actually fuse two defects to make defects of higher strain. So this is a movie showing that we have two elastic dipoles. These are the point defects, and again I can use laser tweezer to fuse these two -1 defects and to form a non-singular defects of strength -2. Okay, that means this is a ring defect between two particles. So this is a sort of topological defects of charge or the topological charge -2. So this binding is quite strong. Okay. Now again we since the particles they have a long range interaction, but then we need to guide them to make some useful structure. So in this movie I saw that if I use a laser tweezer, okay, and I direct these particles to form sort of linear chain, and I can make several chain, and then those chains can be actually oriented in anti-parallel manner to make sort of two-dimensional colloidal assemblies. So now, so this is basically a small, it's a demonstration of a 2D, how we make a 2D colloidal crystals. Now, if you look at a chain, so these chains, these are the particles, and between the particles there are some defects. So these are the point defects. So these point defects actually give rise to a short-range repulsion, and then the elastic forces are attractive and long-range attractive. So you have a long-range attraction and short-range repulsion, and the balance of these two forces give rise to a stable structure. Okay, and two such antiparallel chains can be arranged, and then we can make this for a 2D crystals. Now, using the various types of defects which I have shown in the previous slide, we can actually make colloidal crystals with complex architecture. For example, this is the building block for this 2D assembly is an elastic dipole. That means particle having a point defect. So this is the optical polarizing microscope texture. You can see the beautiful color comes because of the biodefinition of the material. So this also tells you that you have a strong elastic distortion in the medium. Okay. Now in CCT, yes, they are much beautiful, and so we can schematically show that how this point defects is shared by these particles, and the structure is stable. This is again a 2D assembly made of particles having ring defect, and this is a optical polarized microscope image, and this is image with CCD. And again, you can see each particle is dressed with a ring defect. Okay, and this structure is also stable. And this is schematic representation how these particles are actually connected. So again, we can now actually use the combination of the elastic dipole and quadrupole. Yes, we can combine elastic dipoles and quadrupoles, and you can see that using a 2 dipole and a quadrupole, that means we can actually, so this is a base unit, and assembling this base unit, we can make a very complex colloidal crystals like this. And this is, of course, the polarized microscope textures, which is much beautiful, colorful. And again, this is another 2D crystal made of non-singular defects. In this case, this is colloidal dimers. The 2 particles are basically bound by this defect ring of topological charge -2. Okay, and this texture, as I said, this colloidal structure are very stable because the binding energies are several thousand kBt. Even several days, months, they can stay without any problem. And so another interesting aspect of this, that this what happens to the defects when we change the phases. That means liquid crystal exhibit variety of phases, right? So let's say we have a phase transition. Now, how these defects actually evolve across the phase transitions, I can show in this movie. You see, I have a topological dipole, and as you decrease the temperature, go to a symmetric phase. That means the now liquid has a layered structure, and you can see the point defect disappear. In place of that, there is a line defect. So this line defect, and in this line, basically, this is what happens. Symmetric layers, that is these molecules, they are tilted in the opposite direction, and this structure can be reversibly changed between this structure and this structure. Okay. Now, one important consequence of is that suppose we make a 2D crystal, and then we decrease the temperature. So this is made in the nematic phase. I decrease the temperature, it goes to another liquid crystalline phase, but it's called symmetric, where you have a layered structure. Now you can see that crystal, there is a structural transition in the 2D colloids. Okay, and this structural transition in the colloid is driven by the phase change in the medium. Okay, and so this I'm not going to detail, but the question is what actually happens, that if you look at, let's say, 2 particles and study the interparticle separation, we actually find out that these interparticle separation shows some discontinuity at the phase transition. So they show some sort of critical behavior before and below and above the phase transitions, and that is, they basically demonstrate how the elastic constant in the relevant phases vary with the temperature. Okay. Now, this colloidal interactions can be tunable not only by temperature, which I have shown, but also by electric field. So this is one demonstration of a 2D assembly where this I have used a colloidal dimers which is bound by a ring defect, which is non-singular defect of -2. And now, if we decrease the temperature again from nematic to symmetric phase, that means I am changing the temperature. I am manipulating these colloidal interactions, and you can see again there is a structural transition in these 2D colloids. Okay, this structure is completely different than the initial structure. Therefore, this by going around the phase transitions, not only we manipulate these topological defects, but also we manipulate this changing in colloidal interaction. Now, the same structure, if we now apply electric field, we see that when we apply electric field, this colloidal, there is structural change again. In fact, this lattice parameter can be tuned by applying electric field, which is perpendicular to this plane, or nearly 35 to 40%, which is not possible. Such a large tuning of this lattice parameter is not possible in any solid crystals. Okay. Therefore, this kind of tunable structure is very, very useful for many applications. So to summarize in my first part, I would say that we have actually demonstrated how topological defects of liquid crystals, which are unwanted in liquid crystal displays, can be exploited for making large colloidal crystals, which are also stabilized by long-range elastic forces, to make a complex crystalline structure with crystalline structure. Okay, and such structure or colloids are useful for photonic crystals and even maybe for metamaterials. Okay. Now, in the second part, I will talk about the active particles. Okay, so these colloidal particles in liquid crystals become active when you power by electric field. Now, as you know, these active particles have been studied, very intensively in these days, because these active particles can mimic this living microorganism, and therefore it is these active particles and their collective study is very useful for understanding the collective dynamics of living materials and also some problems in non-equilibrium structural mechanics. Okay, so these are some natural active particles. This is example of an algae. This is called Chlamydomonas. You can see that they, in a solvent like water, they move around. Okay, and they are self-propelled particle. And this is E. coli bacteria. This is also a self-propelled particle, and they randomly move in the medium because of the food or reproduction. Okay. Now these are called microswimmers, but they have some very different swimming principle. For example, these Chlamydomonas are called puller type microswimmers. What they do actually, they have flagella. You can see they have flagella. They continuously beat in the fluid with the flagella and create some local flows surrounding them, and that flow is towards the body of this object. So as you can see, this arrow shows the flow is towards the object. Okay, this is also demonstrated by this, the blue arrows. So if the object is creating a local flow like this, which is towards the body or towards the object, these are called puller type microswimmers. Whereas E. coli, you can see, is a sort of a pusher type, because it creates a flow, and the flow has that the flow is pushed out, okay, pushed away from the body. These are called pusher type microswimmers. Now the question is, it is very difficult to study the behavior of this particle, or at least in the physics lab, not easy to study such living microorganism and do the control experiment in the laboratory. So now question is it possible to make artificial active particles which can mimic such systems? Yes, there are many different types of ways of making the artificial active particles. For example, we can exploit electrophoresis, magnetophoresis, thermophoresis, chemotaxis, phototaxis. So these are the different techniques. So some examples are, this is a polystyrene particle which is coated half with platinum, and this is hydrogen peroxide. So the platinum is a catalyst, and it reacts with hydrogen peroxide and decomposes into water and oxygen. Therefore, there is a gradient of the hydrogen peroxide across this particle, and therefore the particle is self-propelled. Okay. So this is some sort of example of a chemotaxis. Now this is a thermophoresis. So this is again the particle. This is dielectric, and upper half is the metal. It's a gold coated. If you use or you shine with a defocused laser beam, and such that this metal absorbs the laser light and get heated up. Therefore, there is a temperature gradient across this particle, and therefore this particle can move, randomly in the media. And also this kind of silica, chiral silica particles coated with magnetic layer, they can move under magnetic field, and this particle can also guide it. Okay, so these are some examples of active particles which have been studied very rigorously. But the main, in fact, there is a nice review article which is published quite recently. Now, the one main problem of such active particle is that it is very difficult to control the direction of motion or their motility. Okay, so it is very difficult to control their motility. So can we control the motility of such particles? Now, as I said, another technique which is very frequently used, rather extensively used for transporting particles, is called electrophoresis. So that is, in fact, used even in the industry. So this electrophoresis could be two types, called linear electrophoresis and non-linear electrophoresis. This is some common thing which many of you know, but I just for the sake of some students, if they are present, that in linear electrophoresis, if you have a charged particle under electric field, they so this charged particle, they attract counter ions, positive charge, and when you apply electric field, the positive charge moves in the opposite direction. So there is a flow, and this flow is called sleep with the velocity is called a sleep velocity, and that sleep velocity is proportional to the linear to the electric field, and it depends on the zeta potential, surface potentials called zeta potential, and the viscosity. And this is a standard electrophoresis, linear electrophoresis, and it is known for years. Now, another type of nonlinear electrophoresis is observed, that if the particle doesn't have charge, but they are polarizable, that means if you apply electric field, the particle get polarized, for example, the metal. So then once it is polarized, it attracts opposite charges at the surface, and those charges can now respond to the electric field and creates a local flow. For example, if you have a gold particle in electrolyte, and then you can see there is a flow field, which is symmetric. And this is a sort of velocity field imaging. You can see that the flow field around this particle is symmetric. Okay, there are 4 vortices, but the flow field is symmetric. So this particle will not move because of this motion of the fluid. This particle will move, but this particle will not move. But if you break the symmetry of the particle, that is making one surface asymmetric, then this symmetry is broken. The 2 lobes vanishes, and such particle can be motile. In fact, there are several interesting papers by this group, and so it shows that this velocity is proportional to E square. Okay, this is a quadratic. Okay, so that means the velocity does not depend on the polarity of the field, unlike the first case. Okay. Now, if the electrolytic medium is liquid crystals, then things are completely different. As you know that I said in the beginning that in liquid crystals, such particles induce topological defects. Okay, and liquid crystals, they have impurity ions, therefore they are weak electrolytes. Okay. Now, when we apply a electric field, so what happens that this is the particles with a ring defect. The red is a ring defect. These charges on the electric field, they tend to move from left to right, but they are collected in the distorted region. So these lines are basically the molecular field or the directed field. Okay, these lines. So you can see the charge, there is charge accumulation. Those accumulated charges, they respond to electric field and create local flow like this. Okay, so this is a flow field map. Okay, and again, we can see that there are actually 4 big lobes, vortices, and there are small vortices around. But if you look at the X and Y plane, they are symmetric. Therefore, such particles or the particles in the liquid crystal having a ring defect will not be motile because the flow is symmetric. Okay, to make this particle symmetric, you have to break the fore-aft symmetry of this flow. But now, if you look at the elastic dipoles, which have the point defect, here we can see, and this is the direct fields around the particle. We can see that this presence of the point defects breaks the symmetry of this flow. So flow is stronger on this side compared to the back side, which is again can be seen in experiments. The flow is stronger here. There are 4 vortices, but this is not symmetric. And such a particle, if it is free, it will move in this direction. Okay. Therefore, particles having elastic dipoles or having a point defects can move in the liquid crystals along the director. Okay, along the director. And these 2 basically were discovered quite some time ago. Now, our aim was to that, okay, how can we make this particle motile, not only motile, but can we control the direction of motion? So what we did, actually, we designed what is called Janus particle. That is, we took a dielectric particle and half side of the particle coated with a metal, the dark region. And this is called Janus particle in similarity with the Roman god Janus, who is having 2 faces. One sees the future, another sees the past. Okay. And it's very simple to make such particles. Basically, you start with the silica particle and deposit sort of titanium and then again silica or so, then you can get a Janus particle. These are some microscope, wide field image of this taken from microscope. You can see the dark one is metal and this white one is basically silica. Okay, so these are the Janus particles. Now, when you have a elastic dipole, so this is the elastic dipoles, and these 2 dipoles are oriented in the opposite direction, you can see apply in the in-plane field. Of course, this particle move in the opposite direction because of the dipole orientation. So this is fine. But if you look at and compare their velocity with respect to the non-Janus particle, that is the pure silica particle, okay, the velocity of Janus particle is much larger, 4 to 5 times larger, okay, than non-Janus particle. The question is, how do you understand such a large velocity? So if you look at this, the best way to look at this surrounding the fluid flow patterns. Okay, so these are the streamline. These streamlines are generated by dispersing some quantum dots. Okay, and look at this fluorescence image movies, okay, under the microscope and track this particle and see how is the flow field. This is how this flow field is generated. So you can see if you have a non-Janus particle, so this particle has a point defect here, this is a defect, and there are 2 big lobes and there are small lobes, and this particle of course will move in this direction. So if you have a Janus particle, then this symmetry is further broken. These 2 small lobes are the vanishes. And more importantly, you see the velocity in this metal surface, which is much higher, almost double. This is 0.07 micrometer per second. This is 0.16 micrometer per second. That means the velocity on the metal surface is much stronger. That is why this Janus particle moves with a much stronger velocity. Okay, this is fine. But now there is some important questions. Now, when this fluid is flowing, there is a flow. Does it affect the director or this molecular field? So I will not go into detail, but simply I can say that if we calculate the Ericsson number, which is basically the ratio of this viscous force to the elastic force to the viscous force, and Reynolds number and Peltier number, all are very, very small. Therefore, this flow does not actually disturb the director field. Okay, inertia also has no role in this effect. Okay. Now, this something very interesting happens when you look at this quadrupolar particle. That is, particle having ring defect. This is Janus particle having ring defect. You please recall that in the previous two slides, or in two slides, I have in the two slides before I have shown that if you have ring defects, this flow field around the particle is symmetric and the particle will not be motile. They will not move. Okay, in liquid crystal. But if you see here that when I have a quadrupolar particle and just a Janus particle, this Janus particle move facing the dielectric hemisphere. Okay, it's just repeating the movie again and again. Now, so this is in a plane, so electric field is applied to the plane, and I'm seeing here. Okay. Now, so if you have a Janus particle having ring defect, quite differently oriented than this particle. So in this case, metal surface is up. You can see this particle move up, facing the metal hemisphere. So this particle is moving facing the dielectric hemisphere. This particle is moving up with the metal hemisphere. This particle is moving down with the metal hemisphere. Okay. So these are the two 90-degree orientation or defined movement. One goes along x-axis, one goes along y-axis. Now, if you look at the particles which have defined orientations, for example, 45 degree with respect to xy direction. Now, if you see this particle, it goes, see, metal-dielectric interface is making some angle, nearly 45 degree or so, with respect to this y, or 135 if you say with the x-axis, it goes in this direction. Now, similarly, this particle goes in the downside direction. Okay, and this particle moves in this quadrant, and this particle also can move. So, what is observed here is that the quadrupolar particles, that is, particle having certain defect, which in general doesn't move in the liquid crystal, just because making them Janus, that is asymmetric surface, this particle can move in the 2D plane in all directions, depending upon how the metal dielectric hemisphere is oriented. Okay. Now, if you look at the summary, is that this Janus particle can move in all directions in a plane. Okay. Therefore, we can actually have omnidirectional transport. So you can see this particle having metal hemisphere move in this direction. As you move, this defined orientation can give rise to different kinds of motion in different angles. Okay. So therefore, if we have we can actually even sort of understand from this point of view, is that we define a Janus vector S, which is perpendicular to this plane of the Janus plane of this metal-dielectric interface, and by varying S, this angle phi from 0 to 360 degree, we can achieve all this orientation. Okay, in the plane, and with this we can achieve complete sort of transport in all directions. Okay, therefore this is a beautiful example of omnidirectional transport of particles in a plane. Please recall, such transport is not possible in an isotropic solvent like water. Okay. Now, not only that, another interesting aspect is that the direction of motion of the particle can be controlled by remotely by controlling this amplitude of the field. So you see, I am changing the amplitude of the field from 1.5 to 2 volts per micrometer. Whenever I am changing recursively, the direction of motion is changing. Okay, of the particle. Okay. Therefore, I can change the direction of the motion of the particle remotely by changing the amplitude of the field. Similarly, by changing the frequency of the field, I am changing the frequency from 30 Hz to 50 Hz. Okay, see, this number is changing. The moment I change the frequency, it becomes slow, but it still changes the direction. So I am recursively changing between 30 Hz to 50 Hz, and whenever I am changing, you can see the particle is changing its direction of motion. Okay. So, so the question is, what determines the navigational ability of this particle? See, this kind of navigation is, again, I stress, this kind of navigation is not possible with any isotropic solvent like water or any other thing. Okay. Now the question is why this kind of navigation abilities are there. I'll not go into detail, but I can simply tell you that if you look at the velocity component of the particle, we find that for Janus particle, the x component of velocity, okay, is greater than the y component of velocity for a given field. Therefore, when you change this electric field for some value, the relative change in this x component is much larger. Therefore, theta or the orientation angle is changed. And opposite effect actually happens in case of frequency dependence. Okay. Therefore, by changing the frequency and the amplitude of the field, we can remotely control the direction of motion at will. Okay. Now the question is, how do we understand such motion? So this can be actually this work done in collaboration with Sridham and his group. So basically, we calculated the electrostatic force density around the particle. Let's say this is a particle and this is a three-dimensional elastic distortion with a ring defect. Okay, if we calculate the electrostatic force density, this force density has two parts. One is that this involves the physical properties of the liquid crystal, dielectric anisotropy, okay, and conductivity anisotropy, and this is the Green's function operator, which is positive, and this is the quantity. So if you look at this quantity, which involves most of the physical properties of the material, and our material delta is negative, therefore this quantity is positive. Okay, therefore this sign of this force density depends entirely on the quantity in this bracket. Okay, now if you look at in this bracket, what happens? The force density depends on the change of theta with respect to z direction. Okay, the gradient of or the variation of theta with respect to the z axis, and similarly variation of theta with respect to x axis. These are basically called splay, and this is called bend deformation. And psi is given by this expression, and the lambda is 1 for conductor and is less than 1 for dielectric. Okay, therefore the force density is larger for a conductor and smaller for dielectric. So what is more important is that this quantity in the bracket determines the sign of the force density. Okay, and if we actually put this sign in this fourth quadrant, okay, in fact, let's say if the particle is moving in the x direction, then we have to see symmetry breaking in the zx plane is relevant. So zx plane we look at. In the zx plane, what is important is this particle, the del theta del that is changing. So you have a splay, mostly splay dominated except these 2 points. This is a splay. Now when we have a splay, we find this force density is towards the particle. The direction of the force density is direction of the particle. That means the flow is like this. Okay, so this is like a polar type. Okay, now this is a polar type. Now this flow, since this part is a metal, and this metal will induce more charge density in this side, therefore the flow will be stronger. Now you can see the symmetry of this flow is broken. This is stronger flow, this is a weaker flow. And the particle in the particle can move facing the dielectric in the x direction. This is what exactly is seen here. This particle moves in the x direction facing the dielectric. Okay, and this is a polar type. But now, if you look at this particle when it is moving, which is moving along the y direction, in that case, you have to see the symmetry breaking in the yz plane. Okay, this is a 3D, but look at the symmetry in the yz plane. In the yz plane, we see the dialectic field around the particle is bend type. That means this term is not relevant. This term is relevant. Okay, and if you put this proper sign in the fourth quadrant, we find that this force density is basically given by these arrows. So in this case, again, that in this case the flow is basically away from the particle. Okay, and you can force density direction is up and this is down. It's opposite. Now again, since this side is a metal surface, flow is stronger and symmetry of the flow is broken. And this kind of flow is called polar flow with respect to the electric field direction. And this particle will move facing metal hemisphere. This is what exactly you see. This particle moves up with the metal hemisphere. So this particle is called pusher type. Okay, they are basically mimicking that E. coli and this the algae, that Chlamydomonas algae, polar and pusher type. Now other intermediate orientations can be hybrid. That is, they are both polar and pusher types. Therefore, what we have demonstrated is that these particles in liquid crystals behave like a micro swimmers, and we can control the direction of motion by changing the external electric and magnetic fields. Okay, this is again very interesting because this is the active particle where you have complete control on the motility. And so another interesting sort of defect I will show here, that now in the previous case I have shown that symmetry of the surface is broken and we saw all exotic transport properties. Here I show you a particle which is it's called a snowman type shape particle. So you have a bigger sphere and a smaller sphere. and total length is around 3 micrometer around the axis. And such particles, when you disperse in the liquid crystal, you see they show very exotic sort of defects. And if you analyze, we find that you can have a point defect on the bigger lobe, or you can have a point defect on a ring defect on the bigger lobe. You can have a ring defect, the bigger ring on the bigger lobe, and also a small ring on the small lobe, also a point defect on the smaller lobe. So, in fact, it is possible that this point defect, can be topologically transformed, move from left to right. So, point defect can open as a ring. The ring can slip from bigger to smaller lobe, and from smaller to again outside this one, the point. This conversion is topologically allowed. So we see beautiful defect polymorphism just because of the shape. But then this defect polymorphism gives rise to very interesting transport properties. For example, if you look at their velocities, defined particles having defined topological defects, the defect polymorphism, you see the velocities magnitudes are very different. Not only that, you see the direction of motion is also different. For example, when the point defect is on the bigger lobe, this particle is a pusher type, it moves in the left side. When the point defect is on the smaller lobe, this particle again a pusher type, but moves in the opposite direction. And when this point defect opens as a loop, like a loop, this is bigger loop and smaller loop. These are the puller type, and their velocity is small, but they go in this opposite direction. Therefore, this is another example where this defect polymorphism can control this the mobility of this or motility of this particle. Another interesting aspect that we can show that again this case we show that how this transporter particle can be controlled just by changing the frequency. You see, this particle is moving forward. Now I change the frequency, it's moving backward. Again, I want to move it to the forward. I can change the frequency. So this is a complete control you have, and again it is remotely controlled. And by applying a one-dimensional field, you can have a motion control motion in the 2D, which is indeed remarkable. Now, this is the last slide. Here I show that these particles can also show various other types of quadrupolar defects, where these particles can change their orientation, keeping the ring vertical. So this is a ring defect, and this ring is perpendicular to this symmetry axis of this. You can see these are the elastic distortions created by different types of defects. So we can find out that these defects actually are this kind of defects. Now, what is the importance of this kind of defects is that what we observe is that these particles actually, when you apply electric field perpendicular to this plane, depending upon the tilting of this particle with respect to the defect loop, this particle can move in different directions. See, this can go to this direction and all kinds of, again, we can achieve omnidirectional transport. So here, so I saw this one movie where I have small video clips actually of individual particles of defined defects, and they are combined, and you can see that this particle can actually be transported in various directions. By applying a unidirectional field which is perpendicular to this plane. So to summarize, I would say that in this talk, basically I tried to show you that we have created a controllable active particles which acquires motility in the liquid crystals by transducing the energy of the imposed electric field. And so what is more important is that we have achieved complete command, which is not possible in any other systems. And this kind of command is useful for active metal control, transport, targeting, delivery, and various things. So, so to summarize this, I can say that in this talk, basically I demonstrated that how a topology or topological properties can be exploited for the case of liquid crystals to make useful structure, which find some useful applications in complex systems. And with this, I thank you for your kind attention. Now I am ready to take questions from the audience.
So thank you, Professor Dhara. And the talk is open for discussion now. So if you have any questions, you can type in the chat box or raise your hand. For participants who are on Zoom, on YouTube, you can just type in the comment box and then we will take it up.
Someone is asking question. I cannot hear.
No, I think I'm just looking at the YouTube. But okay. Maybe I'll start with couple of naive questions that I have, and in the meantime, maybe other participants will be asking. Uh, I was just wondering, so the speed of these particles, it was mentioned that it's about 0.15 micrometers per second, right?
No, these particles actually can move depending upon the field strength. See, the velocity of these particles, it varies quadratically with field. Okay.
Okay.
So let me show you. For example, you can see in this. Okay, in this you can see here. This velocity is around 12 micrometer per second. Okay. So this this is nonlinear electrophoresis. Velocity varies quadratically. Okay.
Okay. So how does this compare with because these particles are actually moving in a liquid background, right?
Yeah, this is
so how does it right? So how does it compare with the thermal agitation within the background?
See, if you see that if you don't apply electric field, okay, then you can see the boundary motion of the particles. Okay.
Right.
Okay. So, but then the resultant displacement is zero. Right. So, but then when you apply electric field, then you can see they move with this kind of 10 to 50, 20 micrometer, even more depending upon the field and the size of the particles. So, therefore, it is much larger than this. The velocity you need to get the
Brownian.
Yeah.
Okay. So I guess I'll just continue with a couple of more. Right.
Yeah. Sure.
So when we apply this electric field, and we can understand that how the particles move. But then, what would happen if we just apply a DC field?
See, this is a good question. Note that these particles are not charged. Okay. Therefore, since they have no charge, if the liquid crystal, if you heat and go to isotropic state, like isotropic liquid, right? Because liquid crystal can be heated to a high temperature, and where the order is destroyed, it becomes isotropic liquid. And if the particle has no charge, you will see the particles are not motile; they will not move. Okay, and so if you apply DC field, if there are no charge, they will not move. But if they have charge, they will move. But these particles have no charge. Therefore, no movement will be observed. Even in liquid crystals, if you apply DC field, they will not move.
Okay. So just related to that, so is there a critical value of this frequency of the AC field in terms of the response of these particles?
Yes.
That beyond which we may not get this kind of a uniform.
Yes. Yes. In fact, I have. Let me show you. There is a frequency range within which this motion can be observed. I think I have one. Yeah. You see that frequency range of the frequency window is up to 60 or 180 hertz. Okay. So this frequency actually is related to the two time scale, which is the particle charging time and the electrocharging time. Okay. So this is because that is so that everything happens within this short time scale, and this is connected to the particle charging time and the electrocharging time. Yeah, because this is electrophoresis. Yeah.
Right. Okay. Thanks. So I guess there is one question from Saptarshi. Yeah. He's asking, are 2D structures the my software analysis, and what could be other stimuli to have such controlled behavior, such as elastic plastic deformation?
So can you repeat these questions once?
Yeah. So I think he has written the chat box, so it would be easier for you to. Yes. Oh, sorry. I think he sent me direct message on. Anyway, I'll repeat it again. So are 2D structures the premise of the analysis? Right. So basically, this is all happening in a planar sort of geometry.
Yeah. This is a 2D. Right. These are all 2D structure.
Right. So what could be other stimuli to have such controlled behavior?
What?
Let's say other than the other than the electric field, could
Ah.
there be other stimuli to
Okay,
get this kind of motion?
these structures are stabilized. Okay, this structure, colloidal structure is stabilized due to the two competing forces. Okay, there is one short range forces which is basically see that these are the defects. The defects will not allow these two particles to touch. So they are because the defect is shared by two particles. Okay, so there is short range repulsion, then the long range elastic attraction. So these two forces basically balance to have a stabilized structure. So this structure is stable because of these forces. Now, if you heat this structure, if I understand your question correctly, this is stable just because of the defects. Okay, once you remove the defects, the structure will break. Okay, and this, how can we remove the defect? We can heat the liquid crystals, go to isotopic state, and the defects will disappear, because the defects are basically, they appear due to this Bookend symmetry, or the symmetric phase transitions, right? So therefore, the defects will disappear, the structure also will disappear. And this structure, once you make, okay, so see how I made this structure. I basically use these particles and use the laser tweezer to guide and make this 2D structure. This structure is stable. Okay, there is no external force is applied to hold this structure. This is completely stabilized. This is stabilized against thermal fluctuations. Okay, because the binding energy is up to a few thousand kBT. Therefore, this thermal fluctuation cannot break the structure. So this is stable structure and no external force is required. Now, external electric field I am applying to actually show that the external electric field can actually change, can tune this lattice parameter. Okay, that is the aim. Okay, so this is one of the way that we can have a large lattice parameter change. Okay, so here the defects did not vanish. Actually, the defects are highly compressed. Okay, so but this is again to demonstrate that this structure can be sort of tuned to some extent by applying external field at temperature.
Okay. There's another question by Devesh Ray. So he's asking, like, what is the background? Background liquid in which these Janus particles are stabilized. So because as you mentioned, why water-based solutions cannot be used?
See, this background, all this what which I have presented here, the background fluid is liquid crystals. Okay, right? And now it's a good question. Why it cannot be done the similar thing in isotopic liquid, the other solvents? Okay, please remember all the credit goes to these anisotropic physical properties of the liquid crystals and the topological defects they induce and your ability to manipulate them. So if you have isotopic solvents, there is no defects, correct? Therefore, and there is also the liquid crystals, they have elastic interactions. In isotopic medium, we don't have elastic interactions. Then what is the binding forces? In isotopic medium, you have binding forces just short range, which is maybe van der Waals or steric or Coulomb, but you don't have much control on those short range forces. Here, I have a long range forces. Long range in the sense 4 to 5 times longer than the particle size. Okay, and I am conveniently able to guide those particles to make the structure. Okay, so all the credit goes to these anisotropic physical properties of the liquid crystal. That is anisotropic, the elasticity, dielectric constants, the dielectric anisotropy, and the conductivity anisotropy, and these topological defects.
So, are there any more questions? It doesn't look like. Okay, so if that's the case, then let me thank Professor Dhara once again for taking time out on a Saturday and exposing us to this wonderful world of liquid crystals and anisotropic behavior. And also thank the audience who joined us on Zoom and on YouTube for this talk. And again, I would also like to thank IPA once more for selecting IIT Kanpur for hosting this colloquium. It was a wonderful experience. So thanks a lot. And with that, I'll close this session for today. Thank you. Thank you.
Okay, thank you all for kind attention, and thank you, Professor Nanal and Aditya, for this for the invitation. Thank you very much. So now we can leave the meeting.
Yeah. I think I think as Vanna said, we can
Vanna,
probably
is
close
allowed?
the session now. I don't think so.
Yes, sir. Okay, so you are the host. You can close this.
Yes. Okay. So thanks a lot, and
Okay, thanks.
hopefully, I mean, you can visit us sometime now in the near future, and we can have a one-to-one interaction within the department itself. Right. Okay.
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 Thank